Systems with one energy storage element, like RL and RC circuits, have input-output equations that are first-order differential equations. We've already seen how to write the differential equations governing first-order circuits. In this video, I'll talk about solving first-order differential equations. The differential equations I'll solve in this video will all be linear, first-order, ordinary differential equations with constant coefficients. These equations allow us to model circuits with one energy storage element. All of the elements in the circuit have to have linear voltage-current relationships, and the properties of the elements can't change with time. So resistances, capacitances, and inductances are all constant values. I'll write my first-order differential equations in this form. The multiplicative factor on the highest order derivative is 1. That means that the multiplicative factor on the 0th order derivative is 1 over the time constant. The right-hand side of this differential equation is called the forcing function. It's a term that models energy addition to the system, so it'll account for voltage and current sources in our electrical circuits. In order to solve a differential equation, we also need an initial condition, which is the value of the output at some time. In physical terms, this defines the energy stored in the system at the time t0. Remember that a differential equation governs the energy stored in a system. The forcing function, u of t, defines the energy being added to the system, and the initial condition provides the system's energy at some time. This means that the problem statement gives us the energy at some time, the energy addition after that time, and the equation governing how quickly the energy in the system can change. For now, I'm only going to look at the solution to first-order differential equations if the forcing function is a constant for times greater than 0. In this case, the form of the differential equation for time greater than 0 is dy by dt plus 1 over tau times y is equal to some number, which I'll call a. The initial condition is that y at time t equals 0 is some number y sub 0. Our goal is to solve the differential equation to find y of t for times greater than 0. Y of t is just the solution to the differential equation here with this initial condition. In the case where the differential equation describes a system, such as an electric circuit, the solution to the differential equation is often called the system response. The solution to the differential equation consists of the superposition of a homogeneous solution, y sub h of t, and a particular solution, y sub p of t. The superposition property allows for any linear combination of solutions to be the actual solution, so the homogeneous and particular solutions can be scaled and summed to get the overall solution. The multiplicative constants, alpha and beta, are the scaling factors on the homogeneous and particular solutions. To determine the homogeneous solution, the forcing function is set equal to 0 and the system's response to the initial conditions is determined. The portion of the solution due to the forcing function is called the particular solution. To determine this part of the response, the initial conditions are ignored. Since the differential equation is linear, these two responses can be superimposed, and this is the complete solution. As I mentioned on the previous slide, the homogeneous solution of the differential equation is the solution due only to the initial conditions. For this case, the input, u of t in our original equation, is set equal to 0. This response is also called the unforced response or the zero input response, since there's no forcing function providing an input to the system. This response is also commonly called the natural response, since the system is, in some sense, responding naturally without outside interference. An important property of any physical system is that its natural response will go to 0 as time goes to infinity. This is due to the second law of thermodynamics, which says that any physical system dissipates energy. Since the solution of the differential equation is describing the energy stored in the system, and since in this case no energy is being added to the system by a forcing function, the initial energy in the system must dissipate to 0 as time goes to infinity. That means that the homogeneous solution goes to 0 as t goes to infinity. Now let's determine the homogeneous solution to our standard first-order differential equation. The forcing function in this case is set equal to 0. So the differential equation is dy by dt plus 1 over tau times y of t is equal to 0. The initial condition is that the value of the function at time t equals 0 is y sub 0. I can rearrange this differential equation to separate the variables y and t. This gives me dy divided by y is equal to negative 1 over tau times dt. To find y of t, I integrate both sides of that expression. To do this, I use two dummy variables of integration. d gamma over gamma is integrated from the initial value of y, y0, to the value of y at time t. The dummy integration variable delta is integrated from 0 to t. d gamma over gamma integrates to the natural log of gamma. If I substitute the upper and lower integration limits, I get the natural log of y of t divided by y0. Integrating d delta and substituting the integration limits just gives me t, so this term becomes negative t over tau. If I eliminate the log function by taking e to both sides of this equation and then multiplying through by y0, I get y of t is equal to y0 times e to the minus t divided by tau. Now let's talk about the particular solution to the differential equation. The particular solution is the part of the solution that's due only to the forcing function. The homogeneous solution goes to 0 as time goes to infinity, and the solution is the sum of the particular and the homogeneous solutions. That means that the solution of the differential equation as time goes to infinity is just the particular solution. For linear differential equations, the form of the particular solution is the same as the form of the forcing function. For example, if the input is a constant, the particular solution will be a constant. Another name for the particular solution is the steady state response. We want the particular solution to this differential equation. The forcing function in this case is a constant. Since the homogeneous solution goes to 0 as time goes to infinity, the solution to the differential equation as t goes to infinity is just the particular solution. So as time goes to infinity, y of t in this differential equation becomes y sub p of t, and this is the equation we have to solve. The particular solution has the same form as the forcing function. So since the forcing function is a constant, the particular solution to this equation is a constant. If y sub p of t is a constant, then the derivative of y sub p of t with respect to time is 0, and this term is 0. If I then multiply both sides by tau, I get y sub p of t is equal to a times tau. Since both a and tau are constants, the particular solution is a constant, which is equal to the value of y of t as time goes to infinity. I'll call this value y sub f for y final. Now that we have the forms of the homogeneous and the particular solutions, we can superimpose them to determine the overall response. If I substitute the homogeneous and particular solutions from the previous slides, the overall solution is this. Since alpha and y0 are both constants, they can be combined to a single constant that I'll call k1. Likewise, the constant beta times y sub f will be combined to a single number k2. In order to find values for k1 and k2 in this solution, we match the solution to both the initial condition and the behavior of the system as time goes to infinity. If I evaluate the equation for y of t at time t equals to 0, the exponent becomes 0, and e to the 0th power is 1. That means the value of y at time t equals 0 is equal to k1 plus k2. Since y sub 0 is the initial condition, that means that k1 plus k2 is equal to y sub 0. Next, I evaluate this expression as time goes to infinity. For t equals infinity, e to the negative infinity is 0, and this term becomes 0. So the value of y at time t equals infinity is equal to k2, which I'll call y sub f for y final. If I substitute yf for k2 in this expression, I find that k1 is equal to y0 minus yf. Since k2 is equal to yf, this is the solution to the differential equation. This formula can be used to determine the response to any first-order linear differential equation with a constant forcing function and some initial condition y sub 0. If you use this formula, though, keep those assumptions in mind. For example, don't use this formula if the input isn't a constant. Now let's look at a graph of this function. It's important to be able to relate the equation to the shape of the response curve, since it can be useful to measure a response and then use that data to estimate a governing differential equation for the system. We know that the value y0 is equal to the value of the function at time t equals 0, and that yf is the value of the function as time goes to infinity. That means that the curve is going to start here and increase to this final value with some kind of exponential shape. The main thing that's missing now is the time constant. If I evaluate this function with time t equal to tau, the exponent here is -1. That means that this function becomes y0 minus yf times e to the -1 plus y sub f. Keep in mind that e is a number, not a variable. This equation can be rearranged as shown here. It's the initial condition, y0, plus the difference between the final and initial conditions multiplied by 1 minus e to the -1. E is a number that's approximately 2.718. So e to the -1 is approximately 0.368. That means that the 1 minus e to the -1 is equal to 1 minus 0.368, or 0.362. So the value of y at time t equals to tau is the initial condition plus 0.362 times yf minus y0. Put another way, tau is the time required for the value of the function to change by approximately 63% of the total change from time t equals 0 to t goes to infinity. The first example I'll do is to solve this differential equation with this initial condition. If I divide the equation by 6, it'll be in standard form. This is a first-order linear differential equation with a constant forcing function. Under those conditions, I know that the form of the solution is given by this formula. Now I just need to find values of y0, yf, and tau. In standard form, this term is 1 over tau, so tau is equal to 2 seconds. y0 is just the initial condition, so y sub 0 is equal to 1. yf is the value of y as t goes to infinity, which is the particular solution to this differential equation. The particular solution means that y of t is a constant. If y of t is a constant, this term is 0. So y as t goes to infinity is 2 times 2, or 4. So yf is equal to 4. Substituting these values into this equation says that y of t is equal to y0 minus yf. 1 minus 4 is -3. E to the -t over tau, which is 2 seconds, plus yf, which is 4. That is the solution to this differential equation. Now let's estimate a differential equation from a plot of its solution. This is the measured response of a first-order system to a constant input. We know from our previous derivation that this is the form of the functions shown graphically. The initial value, y0, is the initial condition of y at t equals 0, which is 16. The final value, yf, is the value of the function as t goes to infinity, which is 4. The total change in the value of the function is 16 minus 4, or 12. 63.2% of 12 is about 8, so this distance is 0.63 times 12. That means that the time constant is the time at which the value of the function is about here, so the time constant is 2 seconds. Since tau is equal to 2, the differential equation has the form dy by dt plus 1 over tau, which is 1 over 2, times y is equal to some number a. Y at infinity is the value of y as t goes to infinity, which is a constant, which means this derivative goes away. So y at infinity is equal to 2 times a, which is 4 from our graph. So a is equal to 2. And the differential equation is dy by dt plus 1 over 2 y is equal to 2. And the initial condition, y at 0, is equal to 16. Finally, let's revisit our previous frying pan example in the context of the solution to a differential equation and introduce some nomenclature relative to dynamic systems. We have a frying pan that's at room temperature, and we put it on a stove burner. At this time, we turn on the burner and apply a constant heat input to the pan. Since the input's a constant, this example meets our criteria for a constant particular solution. There's only one energy storage element, and energy is stored as the temperature in the pan. Due to these conditions, this is the expected shape of the frying pan's temperature response. Since before we turn on the burner, the frying pan is at room temperature, this is our initial condition. The temperature will increase to its final value, which is the particular solution. The final temperature achieved by the pan is also called the steady state response. Temperature indicates the thermal energy in the pan. So when the temperature is constant, the energy is constant, and the heat added by the burner is exactly balanced by the heat transmitted by the pan to the room. The time while the pan is warming is called the transient response, which includes the differential equation's homogeneous solution. Once the homogeneous solution goes to 0, the transient response is said to have died out and the pan's temperature has reached steady state. Now that we've got a formula for the solution to a linear first-order differential equation with a constant input, we don't need to actually solve the differential equation when doing circuit analysis. We just need to make sure that the circuit we're analyzing meets the criteria for the function to be valid. Then we can determine the initial and final conditions and the time constant of the function.